All right. Welcome everyone. This is the ViIRS Information Partnerships May 2026 Wildfire Cluster meeting, and today we have Zeb Becker and Anthony Boyd presenting um, on tracking progression using NASA's new tools. And Zeb is from NASA, and Anthony is from Development Seed. And take it away.
All right. Thank you, Tim. Yeah, great to be here with you all. We're super excited to share more about this work, get involved more with the ESIP community, and I think we got hopefully a good conversation lined up today. So just like Tim mentioned, I'm Anthony Boyd. I'm at Development Seed, and joined by, or I'm here with Seb Becker, and we're going to talk through some work that Zeb and his team have been working on for quite some time. And then we'll be able to share a little bit about some software that we've built to go along with his work to be able to share it more effectively with a variety of different users. And that's really been the impetus for us, crafting this presentation and also getting in front of all of you here. Quickly, some acknowledgments because there have been a ton of different organizations and teams and individuals involved in this work over time. This is a way too short list, so it's certainly not comprehensive. Um, but you can see, across NASA, Development Seed, in different projects and even within NASA, such as FireSense and VETA and MAP. So some of these names and acronyms might sound familiar to you, but there's so much praise and contributions that we could call out on this slide. But as far as an agenda of what we're going to go through, like I mentioned, we'll talk about some of the data and then talk about the software and a prototype tool that we built to be able to share that, and then get into some next steps. And Zeb, I'll pass it to you to talk through this a little more in depth.
Perfect. Yeah, thanks for the intro, Anthony. And as he mentioned, this really is the outgrowth of the work that many, many more people than just Anthony or I have put in. Um, so what we're going to do today is we're going to be presenting an experimental fire tracking product called FEDS, which originally grew out of scientists' needs for large-scale retrospective analyses of fire spread. So FEDS provides satellite estimated fire perimeters every 12 hours for every fire in CONUS, the continental United States, using VIIRS active fire detections. And our record goes back to 2012. So if some of those points sounded unfamiliar, don't worry, we're going to get into the weeds with it. Um, but I just wanted to give a little bit of context for what we're going to get into at this talk. So this work grew out of a longstanding collaboration with the University of California, Irvine, in particular, Yang Chen, Jim Randerson, and some of his students. And as we started developing this science product and sharing more about it, we kind of began to get a lot of people asking, uh, can I get this in near real time? Can I get this continually updating to reflect today's fires? And that's kind of where Anthony and his team at Development Seed came in. So I'm going to talk a little bit about the data. Then he's going to talk about how open source and cloud native geospatial technologies have enabled us to rapidly prototype and iterate on solutions for sharing and visualizing this data and helping to kind of get it out into the world just as fast as it comes in. And then finally, I'm going to talk a bit about an ongoing project that we have, which is funded by NASA's FireSense project to evaluate if feds might be useful in certain operational contexts, particularly looking at roles like fire behavior analysts and long-term analysts assigned to specific incidents. So FBANs and LTANs, if those are familiar acronyms for folks. So I know last month, Mike Pavlonis from NOAA was able to present the NGFS and Wildland Fire data portal to this group, which was two really interesting projects. And I have to say, I've been really impressed by the work NOAA has put in with their fire weather test bed and stakeholder engagements to really put those tools through their paces in real world scenarios. So to set the framing for our talk, I want to say FEDS is a lot earlier in the research and development process. So right now we're kind of moving into the stage of asking, if and how it could be useful outside of our labs, outside of the papers we're trying to write. And I'm really grateful that ESIP has invited us here to talk today because I think this community could have some really helpful insights and expertise around those questions. So I'm going to try to get to the end of this with plenty of time for Q&A. And if anything comes up, I'd encourage you to make a note of it and bring it up or reach out after. So yeah, Anthony, if you'd hit the next slide and the next one. So I want to kind of give a visual of what the Fed's data is. We can kind of see here, so this is the Caldor fire in California in 2021. And what you can see in the jittery frame skipping video here, at least on my end, uh, is that we're using active fire detections to kind of track the progression of this fire through time. So if you hit the next slide and the next one, that was the backup in case the video really didn't work. Um, the backbone of the Fed's product are the VIIRS active fire detection. So this is a mature product that you've probably seen in any number of different places, right? It's in the EGP, it's in WFDIS. This is a screenshot of what it looks like in firms, but this is sourced from the VIIRS sensors on three different polar orbiting satellites, SWOMI, MPP, NOAA 20, and NOAA 21. And what it means when you get an active fire detection from one of those sensors is they have a pixel size of about 375 meters. And if you see a red pixel on your screen there, that means that the sensor has detected a thermal anomaly somewhere within that pixel. It doesn't mean that the whole area is on fire. It's capable of sub-pixel detections. But essentially what you get is this kind of record of what I like to call hot pixels. So those are polar orbiting satellites. So that means we get an overpass about every 12 hours. It typically comes around 1:30 a.m. and 1:30 p.m. local time. So this is already a really helpful resource for fire managers. And then if you hit the next slide. So feds is what you saw in that GIF beforehand. So we're using here an algorithm that's tuned to the underlying fuel type to cluster spatiotemporally adjacent detections into individual fires, estimate the perimeters of those fires, and then track their growth over time. So I like to think of this as adding context on top of the raw active fire detections rather than kind of looking at fire activity from the perspective of, oh man, we had a lot of hot pixels over here today. This allows us to ask questions about how individual fires grow and die out over their whole life cycles and track them at the event level through time as well as space. So next slide, please. So you might be wondering how this compares to other places that you might find perimeters from. So I want to just quickly run through a couple of different sources and kind of give a sense of what level of accuracy we're working with here. So I have a whole paper in prep about this. So I'm going to try to condense a lot of detail into one slide, but I want to kind of build some qualitative understanding of what this looks like. So what you're seeing on this slide in the blue solid outlines, those are final fire perimeters from the monitoring trends and burn severity data set, which is based on 30-meter Landsat data. And I kind of consider that to be the gold standard for systematic remote sensing-based mapping of burned area. But you only get the final perimeter with that. So as you can see, FEDS provides a fair approximation of these fires. And what we found in our analysis was that it performs best for large fires. The rule of thumb I've kind of been using is over 1,000 acres, and it performs better in heavier fuels. This is kind of intuitive. If you think about a fire where you might have one or two VIIRS detections, you can draw a circle around those detections, but it's not really going to give you a lot of additional detail about the shape of that perimeter. In comparison, essentially, it's much easier to see larger things from space uh, when you boil it down to it. So The second point about it being better in heavier fuels also kind of, I think, follows fairly intuitively. Uh, we're getting one look every 12 hours with these sensors that are detecting heat. So in heavy fuels like timber or slash, it's very likely that that's going to continue emitting significant heat for long enough that you'll get multiple looks with that 12-hour overpass time. In contrast, obviously in light, flashy fuels like grassland or shrubland, it's quite possible that a fire will fully burn through an area and be fairly cold, all within one 12-hour window. If that happens, you'll miss it completely. So what we found, again, summarizing very high level here, was that feds had a precision of about 86% per fire. So that means on average, um, of the area that feds says was within a fire, MTBS agreed with about 86% of that. And then recall was 71, which means that feds saw about 71% of the area that MTBS classified as burned. And so that lower recall, if you dig into it more, is really driven by it's actually not bad at all in like timber fuel types, but it's really driven by low recall in those light flashy fuels that we mentioned earlier. Um, so, you know, compared to MTBS, this is a lower resolution. It's more of an approximation of where the fire is. You can really see, particularly in the lower left here, it's a much smaller fire. And you can see at that scale, there's only so much fine detail that you can resolve based on these 375-meter input detections. Uh, the trade-off is that we can get a new perimeter every 12 hours. And so MTBS and all kind of similar uh, high resolution burned area approaches require a pair of cloud-free images from before and after the fire. And because those satellites only come around every few days at best, you're not really able to track the evolution of the fire through time in the same way as you are when you're using active fire detections, which again are based on detecting thermal anomalies or burning at the moment of satellite overpass. So then just two other ones to mention would be GOES, which that's the geostation. Those are geostationary satellites. So they have excellent temporal resolution. Rather than having to wait every 12 hours, you're getting potentially new fire detections every couple of minutes. So those are really strong for detecting fire activity. That's where I would go for early detection. That's where I would go for kind of monitoring the level of activity within a fire from 5 minute to 5 minute intervals. But the pixels that any system makes a trade-off, and the pixels in GOES are so large that it's quite difficult to accurately characterize the perimeter of a fire. You kind of just see like, oh yeah, there's a whole big square somewhere over here, and within that square there's significant fire activity. Then finally, I want to mention NIROPS. NIROPS perimeters are produced by having a plane with an infrared sensor actually fly over the fire. Those are typically going to be higher resolution, more accurate than FEDS perimeters. The trade-off there is that it's on a limited aerial resource, so it's quite expensive to operate the NIROPS platform. And during periods of peak demand, it can be pretty common that it just can't hit every incident that's requesting it. And so you may have to wait for NIROPS, and you may not have it in the early days of the incident before your fire kind of becomes a priority at the national level. In contrast, FEDS images every fire, and it does it twice a day, once around 1:30 and once around 1:30 a.m. and once around 1:30 p.m. So this was originally developed for science use cases, right? Having a landscape scale record of fire spread going every 12 hours, going back to 2012, is going to enable us to study not just the modeled relationships between things like fire weather and fire spread, but actually what actually happened, kind of the observed record. We're really excited about the potential applications on a kind of the more research and development side to evaluate and improve fire spread models. So you can imagine using this data set to train machine learning models as well as to tune and evaluate traditional physics-based models. Some of my colleagues have also shown that it can be useful to estimate burn severity in near real time. So rapidly highlighting areas that are at high risk of post-fire debris flows, like landslides, that could endanger people or contaminate drinking water supplies. So these are a bit more moderate resolution than existing products, but they're available hours to days sooner. Then it's been used to estimate daily smoke emissions for air quality and public health applications. And we're hoping it will also help us understand how climate change is affecting the way that fires spread and predict future impacts on fire regimes. So again, we started out this whole project with science goals in mind. We were wanting to look at the whole record retrospectively, going back to when the first VIIRS sensor launched on the Suomi MPP satellite in 2012, and try to build our understanding about fire behavior at scale with the idea that we could eventually translate that into knowledge that could be handed off to help fire managers, land managers, decision makers kind of create effective strategies to meet their management goals, especially in the context of a changing climate. But at conferences and meetings, we kept getting asked, can I access this data? And of course, with this kind of fire data, it's going to be most useful if you can get it to the people who need it as soon as possible after the satellite overpass and in an immediately useful format. So as we started poking around here, we kind of found that, there are well-established methods to share raster data, like climate model outputs, gridded weather forecasts, and we also know how to efficiently share and visualize relatively static vectors, road networks, parcel boundaries, whatever. But kind of the access patterns that you have with feds data, which are these complex vectors that are tied to objects that evolve through time, and where you really need to be able to link uh, one time step to another and understand how that's changing, doesn't meet a lot of kind of the standard access patterns. And so we found ourselves, as we kept getting asked, can I access this data? Can I access this data? Needing to rapidly develop new methods and interfaces to make the data accessible and useful as soon as possible. So that's kind of where Anthony and his team with NASA's VEDA project, that stands for Visualization, Exploration, and Data Analysis. Makes sense. That's where they've been helping us kind of rapidly iterate on ways to do just that. So, Anthony, I'll hand it over to you to demo a kind of a prototype visualization tool we've been working on with your team.
Yeah, absolutely. And so that's what we've been calling the Fire Event Explorer. And like Zeb mentioned, that's a prototype tool with also backend software associated with it that I'll talk through a little bit here. But to avoid the curse of the live demo and to avoid the curse of Anthony talking for too long, I recorded a video. So there is audio, and let me know if the audio doesn't come through right away or if the frame rate through Zoom is too slow.
I'm not getting the audio. You might need to improv it.
My name Private. Okay, I'll do that. Let me restart, and I'll just talk over the video here. But what we're seeing here on this first shot is, again, the Fire Event Explorer, and this is showing basically footprints. Think of it as footprints for fire activity that we've seen across CONUS. And you can see I can change some of the values here, like fire events within the last month, within the last 3 months, and I can zoom into different areas of the map that might be interesting to me. And so here I'm going to zoom into the southeast of the US to see some of the recent fire activity there. And you'll see more fire events pop up when I expand the date range. Some of the layers that Zeb was just talking through, I can really easily turn on or off and see it update live. But now when I click into a specific fire, this is where I can see the fire perimeter change over time. And I can just kind of let it play and see it grow over time. And I can also prepare a video here. So I'm going to come in here, get my 3D view, and you can see I can change the format to GIF. I can also output a video as well, change the speed of fire growth, so some of the simple variables there. And on the right, you'll also see there's some statistics that we're pulling from the same APIs. So I'm going to jump into this slide because I think obviously I think the prototype is cool. I think the designers and engineers did a great job, and I love playing around with it. So it's like these access patterns that is mentioning. It helps facilitate access to this data, and it gave us a chance um, to test out some different ways for users to visualize and play around with the data. But it's similar to the acknowledgement slide at the front of the slide deck. That was only really possible because of all the open source libraries and standards that Zeb and his team were already taking advantage of, and then that the development team put in place. Things like OGC Features API is what that data is being served up through. Here in the bottom left, this might be a logo unfamiliar to some, but CNG, or Cloud Native Geospatial, is a group that's pushing cloud native geospatial data formats like ZAR and COGS, GeoJSON, all those file formats. Because this data is already in a cloud native format and we're serving it up through a standard OGC API, that last 10%, that last leg of adding a prototype front-end visualization became much more simple. And it also means that this data is like much more interoperable. So if we want to serve this data through a different visualization tool, like VIIRS, and I think Zeb could talk much more to that. We can feed this data into Esri Living Atlas and the places where the people are already working. I think that's what this software that's powering the Fire Event Explorer that you just saw, that's where it becomes really, really powerful. Maybe I'll pause here and see if there's any context that you could add, Zeb, on like where you see this open software stack enabling the next steps that your team want to take.
Yeah, I think it's been really key for us, as you mentioned, that interoperability has been key. So um, we're essentially on the back end, we have this whole data processing pipeline that I work on that goes from as soon as those active fire detections become available. It uses the NASA ESA map data processing system to kind of crunch the numbers and come up with the outputs. And then we dump it all into an OGC, or Open Geospatial Consortium, spec'd API, features API, that's backed by a PostGIS database. And because we do that, the Fire Event Explorer is able to pull from that. But because it's an open source standard that's like really well documented and interoperable, um, other groups are also able to pull from it quite easily and quite programmatically. So, for example, NASA's FireSense site, which I showed you a screenshot from earlier, which is it's a much more of a mature, very popular product that a lot of people are already finding, very, very useful. In fact, I think it's often the most visited domain it's the most visited website in the NASA domain on quite a few days over a given summer. But they're able to just hook up to our OGC API and pull that data into FireSense. And then via the same API, the Fire Event Explorer is hooking up to that. Via the same API, we have a great team at NASA's Earth Information Center that they have these really cool dashboards at NASA headquarters and the Smithsonian, and a couple different NASA centers, I want to say, that are also automatically pulling in this data and creating these scientific visualizations of the largest fires in the world at a given time. So, um, if this was all kind of locked into one proprietary stack, that wouldn't be possible in the same way. So that to me is kind of like a little bit of the magic that's being unlocked here. And then also, as Anthony said, like because we're able to take just like the last couple steps because most of the infrastructure is there, we're able to like really quickly like mock up new ways of accessing the data. Uh, Change them, come up with new ones, swap things in for other things. The alternative to doing it this way isn't really to do it in a more traditional way for like a science team with our scope and our kind of limited number of people to work on this. The alternative is to not do it at all.
I'm glad we got that recorded. I'm gonna quote that in so many places. Okay. Well, I think I'll pass it back to you, Zeb, to talk through the next phase.
Yeah, okay. Now I'm gonna take a more realist tone in this section. So what we've been working on recently um, with the team at NASA is working with fire behavior analysts and long-term analysts. Again, those are F-bands and LTANs. These are fire professionals, typically with quite a deep knowledge of fire behavior, who are assigned to a given fire as part of the incident management team that goes in to manage that fire. And they're responsible for providing to the incident commander, the operations section, the incident in general, predictive analyses of uh, what might happen with that fire behavior. So everything from really near term, like what do our firefighters need to be looking out for this afternoon? What are the risks if this weather system that the incident meteorologist has been tracking does come into play 3 hours from now, all the way out to predicting, potential fire spread over the next 1 to 7 days, all the way out and kind of, identifying potential values at risk, all the way out to trying to figure out when are we likely to get a season-ending event, like a really heavy rain or snow that can kind of conclusively put this thing out, and what kind of risks are we facing in the meantime. So that's kind of what the FBAN and LTAN do on a fire. And we've been working with some really wonderful FBANs and LTANs from across the US interagency fire community to evaluate the potential uses of feds in that kind of operational context. So at this stage, again, we're still kind of asking like, is this something that could be helpful for that type of user? And we're trying to really kind of critically evaluate that, right? So I'm going to share a couple potential use cases that we've kind of co-developed with these folks, and then also kind of highlight some risks. And we're in the process of working through this right now. So this is a bit of learning in public and a bit of my open call to everyone to bring feedback, reach out, please engage. So, okay, potential use cases. The first one is deeply the most obvious, and it's that in some cases this may be the most timely perimeter that we can get. So I'm going to walk you through a couple time steps of an example fire, which is the glass fire that burned in 2020 in California. Um, Around 4 in the morning, approximately, according to CAL FIRE, was the ignition on September 27th. And this fire was already growing quite rapidly by the time CAL FIRE was on scene. And at some point in the morning, they already had it at 1,200 acres. Then at 2:06 p.m., we got our first feds perimeter. That's what you're looking at here. If you'll hit the next slide, please. So the fire really started taking off, and it did not die down during that day-night transition. It had really, really active fire behavior to the extent to which around 11:45 p.m. there was a burnover incident, which really indicates just how quickly this fire was moving. And then right about midnight, we had our first NIROPS flight. So midnight on the 28th, we had our first NIROPS flight. That was about 10 hours after the first Fed's perimeter. And you can see just how much this fire has picked up and gotten moving uh, since then. So I did see a hand. I'll go through the rest of the kind of time steps of this, and then if you'd like to chime in, feel free. If you'd hit that next slide. So what we saw now, what you're looking at is we had a second overpass of Suomi NPP at 2:30 a.m. that morning, and already the fire had advanced significantly beyond where it had been just 2.5 hours earlier. And this is consistent with the Cal Fire incident report. And then at 4:06 a.m., we actually got a third overpass, which kind of happens when the satellite has its first initial overpass where it might be closer to directly overhead, but then kind of sees this on the edge of its scan swath on its subsequent overpass. Um, so you can kind of see that these are all capturing different parts of the fire's behavior and adding on top of NIROPS additional opportunities to capture that possibly just would not have been able to be mapped without that. So I saw a hand earlier. If you'd like to pop in with a question, feel free. Otherwise, we can also do it at the end. Okay, I'm gonna take that as a no. Next slide, please. So that's kind of the most obvious use is it could get people perimeters when they otherwise wouldn't have perimeters, and that can be useful for a lot of reasons. Um, One kind of particular use case that I wanted to call out here was calibrating the fire spread models that FBANs and LTANs use to predict the probability that a fire will spread into different places and kind of predict where it's going to go. So these models are really, really complex. And it's from the outside, talking to these analysts, it's been, and kind of watching over their shoulders as they do this, it's been quite intimidating, just how many things you need to understand and how many knobs there are to turn, uh, as I like to say, to kind of calibrate these models. So that's everything from choosing the specific RAWS weather station that you're going to get your weather stream from, to fine-tuning the fuel models, making adjustments to ERC classes, choosing between different spotting models. Like there's genuinely an uncalculable number of permutations that you can do this. So it takes quite a bit of expertise for them to calibrate their models. But the basic feedback loop essentially goes like this. They take their perimeter for, say I have a perimeter from yesterday and a perimeter for today. So you can kind of see on the left here, um, we took the perimeter, Casey, not me. Um, she's taken the perimeter from, say, yesterday, and then put in the fuels and weather data and all the settings that she's going to use, and then run a model run. So that perimeter is in orange. And then she's run a model run to kind of look and see where that's going to go. Then on the right, uh, superimposed on the outputs of that model run, you see what actually happened. So that's, if you will, the perimeter for today in red. And so at first, with this kind of feedback loop, you might see that your prediction did something completely different from what the fire was actually observed to have done. Then you say, oh, like, okay, maybe I need to tweak this to kind of, I'll switch to a different weather station to take into account the wind direction. I'm going to tweak this fuel model to take into account that I know that it's denser here than is reflected in land fire. Or, again, a million different permutations. The key point here is that these models are very sensitive to having accurate initial conditions. So if you're able to give an analyst two perimeters a day instead of one, or give them a perimeter several hours before they would otherwise have one, that's a real concrete benefit to them. It kind of goes without saying, but the more accurate the spread modeling, uh, the more effective suppression efforts are going to be, the more we're going to be able to take care of firefighter safety. I could go on. So that's use case two. Um, and then if you go one more slide, one other interesting way that we can use this is we can look through our record. So we have it going back to 2012, right? Every 12 hours through all of CONUS. So we can look through our record of historical spread and try to find analogous fires. So those would be fires that burned under a similar combination of conditions, whether that's in similar fuels, with similar weather conditions. You could say, hey, like I need to find a fire that was on a south-facing slope with mixed conifer fuel models in September in, the North Cascades or whatever. And you could then look and see like what have fires in similar conditions actually done in the past. So to kind of give you like a concrete example of what that can look like. There was recently a fire in Florida that was burning in what is usually a swamp. But because Florida is in such an extreme drought this year, the water table has actually dropped below the level of the swamp. And all of what's usually, basically not something it can catch on fire has actually dried out and is ready to go up like a match. So in the standard fuel models, that's a swamp. And if you try to use a standard uncalibrated model to simulate fire spread in the swamp, it's going to tell you, well, it's a swamp. Your fire's not going to go anywhere. So what the analysts who were working this fire realized was that back in 2017, they had another year with a really low water table, and that they actually knew through kind of their experience and institutional knowledge that there had been a similar fire in a similar area under similar conditions. And so what we were able to do was we were able to go pull out from 2017 the Fed's record of fire spread, and then they were able to use that to kind of help calibrate and transfer over their modeling notes from 2017 to 2026. Kind of take some of that hard-won knowledge for over the course of that fire and bring it up and kind of update it to today and use that to tweak their spread models for this fire. So again, I've kind of focused here on this work we're doing with the FireSense program, where we're looking at how we can bring kind of potentially bring these research products into a little bit more applied use. Um, if you go to the next slide, I think it's really important to be clear-sighted about the risks and limitations of this kind of approach. And this is also something I want to kind of bring around to different people in the community and talk through. Um, and again, I'm going to kind of highlight three findings that I kind of find key here. So what I'm showing you here is a NIROPS map. This is not a Fed's perimeter, although it looks similar in that it's just a squiggly red polygon on a map. So the point I want to make about this is that over their years and years and years of experience, responders have seen a lot of fire perimeters on a lot of maps. But those are usually based on either aerial infrared data from NIROPS, which again tends to be more accurate and reliable than Feds, or they'll be from incident GIS specialists who have kind of combined information from whatever ground and air resources they have, including sometimes just sending someone to walk the current perimeter of the fire with a GPS unit, to create their current best estimate of where the fire is. So kind of unavoidably, if you're someone who uses these maps, you have a mental model in your head of what it means to see a line like this on your map. You have certain kind of assumptions and knowledge just built out of your experience about the ways in which those perimeters are usually accurate and the ways in which they're inaccurate. So I kind of view as a danger here, or like something that we need to think carefully about how to communicate. Feds has different underlying limitations and uncertainties. So it's a space-based product. It is more consistently available, but it also has its own uncertainties. It's kind of a different class of perimeter than what you're getting from this. And if we don't make that clear to users, there's a danger that they could see it looking like just another red blob and kind of apply the wrong heuristics to that. So again, to bring a concrete example to this discussion, We recently saw a case of a fire in Florida where ops was using a specific irrigation canal as a holding line. So they're like, we want to try to make sure the fire doesn't get across this canal. A single VIIRS detection appeared on the map to be slightly across the canal, and that made the Fed's perimeter look like it was slightly across the canal. So this is a case where being a couple meters off is really significant. But think back to what I was saying about a hot pixel can mean that there's a fire anywhere in that 375 meter by 375 meter square on the ground. So luckily, in this case, there were already a couple engine crews nearby who were able to visually confirm that there was, in fact, no fire that had spotted across the line. But I think to me, that kind of illustrates this point that we need to make sure we're communicating the kind of uncertainty inherent in like space-based perimeter to people who are used to different perimeter sources. And I think luckily fire analysts tend to have a quite a high level of technical sophistication. So I think they're used to interpreting, flawed models that are all flawed in their own ways. But I think this is really something to think about, especially for communicating to decision makers or the public who maybe don't have that kind of background. If you'll hit the next slide, please. So this isn't really new news, but it's something I want to call out, which is that, of course, there's limitations on the physical sensor. So even though we try to record a new perimeter every 12 hours, the VIIRS sensor can be obscured by heavy cloud and smoke cover. We also know that it can pick up non-fire thermal anomalies like gas flares, cement plants, even the sun reflecting off of solar farms or like large metal factory roofs. And as I discussed earlier, it can also completely miss a fast grass fire. So this is just something to be aware of, and this is a great figure that I've adapted from my colleague Shane Caulfield's recent paper, which I would really recommend if you're interested in it. But it's kind of showing you uh, VIIRS is able to pick up some detections through some amount of smoke, but when you have those really heavy, dense smoke clouds, it's really struggling to characterize the fire activity beneath that. And then that's kind of a physical limitation of this remote sensing pathway, right? There's no amount of clever algorithm tuning that you can do that will completely resolve that tension. Uh, Again, it's just important to be communicating this because if you're putting out a perimeter that says like it has this timestamp on it, say we're looking at like that second column, if you're putting out a perimeter that has that timestamp on it, um, it's important to understand that it may be missing part of that fire activity due to these reasons. And then finally, one more slide. So one other thing that we've heard and that we want to be really cognizant of with this project is that when you're an analyst on a fire, you're already really overloaded with potential sources for information. You're trying to operate in a complex environment, make useful products as fast as you can. So kind of adding another standalone website might not be a desirable end goal. But that kind of does it for so those are kind of some of the risks that I personally have my eye on with this application. Um, I think I'm really excited about the science applications, and I also think that this has the Fed's data have the potential to provide a lot more situational awareness and context to responders, kind of providing an additional layer of context on top of those raw active fire detections. Uh, so I think if we're careful about how we approach this and how we implement it, it could be really valuable. But again, I want to keep this like clear-sighted view of the potential risks and limitations. So if you'll next slide, please. With that, I kind of want to wrap up that part of the presentation, and I'd love to open it up to questions. Um, I'm of course happy to answer any questions you may have. I'm happy to geek out about the kind of underlying data. I would also like to pose a few questions since we're in this phase of gathering feedback and evaluating if this might be useful outside of kind of scientific contexts. Um, I'd love to know if there may be places where you think this data may fall short, or what key factors we should consider for this kind of data to be useful in the field. Also, if you have applications I didn't mention for which you think this data could be useful, I'd love to hear that. Kind of on that note, I'll also just say this QR code and that link go to our website where you can learn more. You can access the Fire Event Explorer that Anthony demoed. You can also access the data via API or via an ArcGIS online integration. So, and then, yeah, also feel free to shoot me an email. More than happy to talk about this stuff. So, on that note, any questions? Would love to get into them.
Um, I've got a question. I'm curious if, like, I think there's something like 22,000 people with NIFC credentials that have access that potentially have access to geospatial content from the NIFC system. There's a potentially huge user community for these kinds of assets. Have you been looking at like what the uptake in the applied community is from this product?
Not quantitatively. So I will say at the moment, it's very early stage. So we're kind of working with individual FBANs and LTANs and one decision support group to kind of start experimenting with this product. So uptake is very low. I think we haven't landed on a final home for where this might be. Yeah. And I'll just mention that this is a kind of an effort that we've started like this year.
I have another one if no one wants to, but I'm curious. There's a rule of thumb that's been circulating in on the West Coast, particularly about 30 and 40,000 acre spread days as being this indicator of extreme severity and and like our biggest mortality patches. Has there been similar kind of things observed within your team as far as like the relationship between spread days and fire behavior?
I think what we're able to look at is the size of that spread per day. And what we're not really able to characterize very well is fire behavior within those 12-hour patches. So I think there's been some great research, particularly if you look at the papers from Jennifer Balch's group or at University of Colorado Boulder, or Rebecca Schulten has a recent paper on multi-ignition fires. She's at University of California, Irvine right now. I think those are really interesting. I think also, Elijah Orland has a paper about burn severity and how it relates to, and he actually used the Fed's data to try to kind of back out like a really rapid estimate of burn severity. Um, that being said, there's only so far we can go with this data specifically in kind of, we don't have the fire behavior side of it, right? We get an instantaneous fire radiative power measurement at the time of overpass, but it can be difficult to go from that to say, and flame lengths were X and, this kind of thing. But I think that's a really important application. If we combine the spread data with additional senses of data on kind of impacts, I think that's a really promising avenue for research.
I guess I have one more on the fire intensity that's actually detected with the VIIRS system. I mean, subpixel mixture issues are kind of ubiquitous in thermal remote sensing, but like how much uh, how much information can you extract within the system from the um, just directly thermal intensity per pixel?
So if I'm understanding your question correctly, the way that Feds is kind of pulling out the going from the raw underlying data from the different sensor bands. Um, Feds makes use of the VIIRS active fire detection algorithms, which draw then, back on the Modis product heritage, even going back to uh, Aster and Aver. I'm saying those acronyms wrong, but it's a little bit so they're using different contextual filters and different kind of combinations of the different band lengths to try to filter out like what is actually a fire thermal anomaly and a vegetation fire thermal anomaly versus a different instance that would just cause like a higher uh, radiation in a particular cell than in the surrounding area. So I kind of view it as like that work is happening more in the previous step. I don't know if that's a satisfying answer, but yeah, Douglas.
Thanks. This is great. And I think in the last meeting, people also brought up firms, which everyone's using firms these days. Have I may have missed it. Is that fast data also being able to link into firms and then having all those parameters in the firm system as well?
Yes, yeah. It's currently on their, it is in firms. It's currently on their experimental tab.
Okay.
It's a little buried in there, but if you actually this link here, if you go in here and click on the thing that says NRT data, near real-time data, has a link to that layer on firms.
Okay. Thanks.
Mhm.
Okay, well, we're coming up on time. That was a really fascinating talk. It was really and it's interesting because we had the NOAA NESDIS content a few weeks ago, and it is interesting seeing these emerge. This it's our tools keep getting better, and it's really great to see your new version, and particularly this vectorization at scale and with high um, low latency. That is really fascinating development. Thank you so much, Zeb and Anthony. This has been a great presentation.
Yeah, thank you for having us.
Yeah, thank you for the invite. Thanks for the conversation.